Okay. How to find a polynomial equation given points. Now, this problem came out of, there's a section in our grade 12 textbook that showed the students how to find the equation of a polynomial given roots and one other point. So, for example, if we have a third order polynomial with these three roots here at, let's say, a, b, and c, and we also had a point here, let's call that at x1 comma y1, where x1 is obviously 0 there. Your third order polynomial would come through here, up here, down here, and have an equation of the form that the function is some number times x minus a minus b and minus c. Well, they shouldn't both be a. Let's call that a capital A. There we go. Where these are the roots of the polynomial. And the general rule is if that's a third order polynomial, you need all three roots and another point, which means in total you need 4 points to be able to uniquely describe the polynomial. Now, what I told my students was it didn't have to be roots. If you had the knowledge that, say, our polynomial was third order, and you had any 4 points, any 4 points will uniquely describe only one third order polynomial. As long as you have one more point than the order of the polynomial, you can fully determine the equation of that polynomial. So I'm going to show you how to do that here. Okay, so consider our problem where we know points So I've got points where x is 0, 1, 2, 3, and our y value is 4, 6, 22, and 70. So I've got 4 points on the Cartesian plane, and I'm going to find a third order polynomial. Now we'd have to know ahead of time that this is third order. You could keep doing finite differences, but then I think you'd quickly run out of numbers because you'd be down to 3 and then 2 and then 1. Yeah, you'd have to priorly know this is a third order polynomial that's fitting these 4 points. What it's going to look like is that polynomial, if it's third order, is going to have some number times x cubed squared x and some other number. So our goal is based on these 4 points to determine the value of these 4 variables. Now we know that if we're looking at our polynomial at 0, that's equal to 0a plus 0b plus 0c plus d, so that's equal to d, and that's also equal to 4. So we know ahead of time d is equal to 4. Our polynomial at 1 is going to give us a plus b plus c plus d is equal to 6. Our polynomial at 2 is going to give us 8a. Now why is that an 8? If the x value is 2, 2 cubed is 8. And x cubed is what's being multiplied by a. So if the x value is 2, our polynomial is 8a plus 2 squared, so that's 4b plus 2c plus d. So you may have noticed I changed the order. I subbed in the value and I put x before the letter. The reason why I did that is all of a sudden these constants are becoming the variables of my system of equations here. And that's equal to 22. And finally, if my point is 3, then I've got 3 cubed, so 27a, 9b, 3c, plus D, and all that's equal to 70. So I now have 4 equations with 4 unknowns, and I've got to work my way through to solve them. Now this is a little bit easier because we happen to have that point where x is 0, which right away gives us a D value. I'm going to show you how to set this up in a matrix, and the way I'm going to show you will work even if that doesn't happen to work out so nicely. So the matrix that's going to represent this system of equations is going to have, I'm going to rewrite this one. My polynomial at 0 has 0 A's, 0 B's, 0 C's, 1 D, and that's equal to 4. So I'm going to put these 4 equations as they're written here into my matrix. So matrix is a box of numbers. I mean, box is not the technical term for it, but it's a, I don't know what the term is. There we go. Okay, so this matrix, assuming we know the order of where everything is, represents all of the information of these 4 equations. Notice I made sure my variables were all in order. A, B, C, D, all in order, all the same order for each of them. I put what all of that's equal to, so I put the y value, the known y value over on the right. These are my known y values. These are my coefficients of D. These are my coefficients of C, my coefficients of B, and so on. This is my first matrix. I'm now going to work on this matrix until I get everything in a form where I've got 1s starting here in a diagonal, and I've got nothing but 0s here. Once I've done that, this will tell me the A value. It'll be 1A plus nothing else will be that value. That'll tell me the B value, 1B, because remember these are my A's, these are my B's, these are my C's, and these are my D's, and so on. So for Gaussian elimination, the work I'm doing to these matrices, I'm allowed to do only 3 things. I can swap any 2 rows. I can multiply any row by any number, including a fraction, which actually means I can also divide it by any number. And I can add any multiple of any row to any other row. As long as I just do those 3 things and nothing else, I can do manipulations that don't get rid of the information embedded in these equations, and I can use this to solve them. So let's go. Strategy here is I want to get 0s everywhere except along this diagonal. So fortunately, this row is all done for me. I'm going to start working on these other ones. And I'm going to get rid of that 8 by multiplying that row by 20. No, I'm going to multiply that row by 8 and subtract this row from it. So I'm going to leave that top row, 1, 1, 1, 1, 6. And this is going to be 0. 8 times 1 is 8, minus 8 is 0. 8 times 1 is 8, minus 4 is 4. That's going to be a 6. That's going to be a 7. And 8 times 6 is 48. 48 minus 22 is 26. I'm going to do the same thing here by multiplying that row by 27. So I get a 0 here. And then 27 minus 9 is 18. 27 minus 3, 24. 27 minus 1 is 26. And 27 times 6 minus 70. 27 times 6 gives me 162. Minus 70 gives me 92. And this last row I'm leaving. Okay, now, if you look at this and you're a little bit unsure, it's nice as you start to write notes as to where each line came from. I got this line by, in the previous matrix, taking row 1, multiplying it by 8, and subtracting row 2. So I got 8 times row 1, and I subtracted row 2. So if I'm circling a number, I'm indicating a row, and if I'm not circling it, I'm indicating a multiple. 8 times row 1 minus row 2 gave us this line. 27 times row 1 minus row 3 gave us this line. Now remember, amongst the three things we're allowed to do, one of them is add or subtract multiples of another line to a given line. Okay, so we're going to keep going. I want a 0 here, and then I'm going to want a 0 here, here, and here. Then zeros all the way here. So I'm going to get rid of this 18 by subtracting 4.5. Yeah, we'll go with halves. I'm going to multiply row 2 by 4.5, and I'm going to subtract row 3 from it. Nothing wrong with dragging fractions or decimals around in here. Okay, so 4.5 times 4 is 18. So that's going to make that 0. 4.5 times 6 gives me 27. Minus 24 is going to give me 3. 4.5 times 7 gives me 31.5. Minus 26 gives me 5.5. And 4.5 times 26 gives me 117. Minus 92 is going to give me 25. So this is 4.5 times line 2 minus line 3. I multiplied this row by 4.5, and I subtracted that row. Why did I choose 4.5? Because 4.5 times 4 gives me 18, and remember, my goal is to get a 0 here. I want zeros everywhere except along this diagonal. This last row I'm going to leave. Okay, so I'm most of the way done. I just got to get rid of these numbers up here. Now notice, I can get rid of that number by multiplying this by some number and subtracting it. The reason why I'm using the one with zeros is when I subtract, because I have zeros here, it's not going to mess with this number. So I've got 1, 1, 1, 1, 6, 0, 4, 6, 7, 26, 0, 0. Now I'm going to take this row and subtract 5.5 times that row. So this is going to be my row 2 minus, no, sorry, it's going to be my row 3 minus 5.5 times my row 4. So I've got 3 minus 5.5 zeros is 3. 5 minus 5.5 ones is 0. That's why I chose 5.5 times row 4. And then I've got 25 times 5.5 fours. Sorry, 25 minus 5.5 fours. So 5.5 fours is probably 22. Yeah. So I'm subtracting 22 from 25. That's going to give me 3. And finally, I've still got 0, 0, 0, 1, 4. Okay, so I just have a few more numbers to get rid of, and then we're done. Okay, we can start working on this top row. We could have at any time. So we've got all those ones there. So I'm going to take 4 times my top row. No, I'm going to use this one. I'm going to do my top row minus my bottom row. So that's going to give me 1, 1, 1, 0, and then 6 minus 4 is 2. So that's row 1 minus row 4, and these numbers are always indicating the previous matrix. Okay, now for this one, let's get rid of that 7. So how about we subtract 7 times that row? So that's 0, 4, 6. 7 minus 7 ones is 0. And 26 minus 7 fours, 7 fours is negative 20. 7 fours is 28, so it's going to give me negative 2. So this is row 2 minus 7 times row 4. This one's done. I can just divide this by 3. I've got 0, 0, 1, 0, 1. So all I did was I took this row and I divided it by 3 to get that. And then this row's done as well. Okay, so we're getting close here. Now I want to get rid of this 6. So I'm going to multiply this row by 6 and subtract it. Going one way or the other doesn't really matter. I don't mind if things turn into negatives. You can always change them after. And let's deal with this as well. I'm going to get rid of this 1. So if I just take this row and subtract this one, that's going to disappear. So we'll do row 1 minus row 3 and put that in row 1. So that gives us 1. So it's these ones here. 1, 1. 1 minus 1 is 0. 0 minus 0. And 2 minus 1 is 1. Okay, so now for this row, I'm going to subtract 6 row 3s from row 2. So that'll give me 0, 4, because there's nothing to subtract. 0, that's 6 minus 6 ones. 0, minus 2, minus 6 ones is minus 8. And then this one's done. And this one's done. Okay, almost done. I'm now going to divide this entire row by 4. So this row is going to be 0, 1, 0, 0, and then 8 divided by 4 is 2, so that's minus 2. Now this row, I'm just going to subtract this row from that one. Now I wasn't doing 2 steps at once before. I hope this doesn't confuse you. But this is going to be, well, if we're looking at from that row, it's going to be row 1 and then minus 1/4 of row 2. Okay, so if you make a note on that and look at it closely, you'll make sense of this. 1/4 of this row, that's a 1, that's a minus 2. It's what we have here. And that's going to be subtracted from this row. So that's going to give us 1, 0, 0, 0. And then I'm going to take minus 2 away from 1. So that's going to give it a positive 3. Remember, I'm subtracting a negative there. And everything else is done. So what I have now, if you look closely, here we have what we call the identity matrix. This is reduced row echelon form. Remember from the initial setup that our matrix was grabbing these coefficients. Right, so we set up that original matrix by grabbing those numbers. So what that means is the first column is the A's, then the B's, the C's, the D's, and then what it's all worth. So the reason why this is so nice is it's telling me that 1A is equal to 3. A is 3. B is equal to negative 2. And because there's nothing else here, it's like B plus nothing plus nothing plus nothing is equal to negative 2, so B is negative 2. C is 1, and D is 4. And remember, the original equation was of the form ax cubed plus bx squared plus cx plus d. So my equation is going to be, my polynomial evaluated at x is 3x cubed minus 2x squared plus x plus 4. I got this from these 4 points. I took these 4 points and I wrote down the equation evaluating the polynomial at each of those x values. After writing a standard form of the equation, acknowledging the 4 unknowns I had, these 4 coefficients, I then took these 4 equations based on the 4 points. That gave me 4 equations with 4 unknowns. I put all the coefficients and the value of these equations into a matrix, and then I kept doing Gaussian elimination to the matrix to get it into this form here with that diagonal of 1s. This grid with the diagonal of 1s, this portion of the matrix we call the identity matrix, and this whole process is turning this into what's called reduced row echelon form. And from that, we could just very easily read off the value of each of those coefficients, and once we know them, we can write down the equation.